Hello everyone. I'm Sudhakar Reddy Narra. I have over 17 years experience in performance engineering. Today I want to talk to you about how we can build reliable high performing cloud applications by applying SRE principles. These days if you see cloud native applications are everywhere. They are powerful but also complex and unpredictable. And that's where the challenge lies. How do we make these systems faster, more reliable and also ready to scale when required? So, over the years, I've helped several Fortune 500 companies tackle exactly that. I'll be sharing a framework that goes beyond just tweaking code or infrastructure. It brings together architecture, engineering practices, and business goals to build truly resilient systems. Let's dive in. So, now that we have seen big picture, let's break down the framework we use to build resilient systems. I like to think of it as a layered pyramid. Each layer builds on the one below it. So, if coming to implementation fundamentals, so for example, in architecture, we focus on clear boundaries like separating, say, order service from billing service using events instead of direct API calls. Basically, this improves fault tolerance and reduces coupling. In code, we prevented, say, N plus one database queries, use async operations where possible, and and also we made sure APIs can handle retries without duplication. And on the infrastructure side, we use auto scaling in Kubernetes infrastructure as a code with Terraform, and also added read replicas to ease database basically read load. So next layer, once the foundation is strong, we enabled performance thinking into our delivery workflows. So we integrated the performance testing into CI/CD and also automated observability and enforce SLOs throughout the lifecycle. This makes performance basically everyone's responsibility, not just a post-production concern. In rail layer 3, after say engineering practices, what we did was like when we implemented these practices consistently, we start seeing the results. Reduced response times or latencies, also improved throughput and better scaling. So system become measurable, predictable, and also tunable. For example, in one case, we brought down response times from over 400 milliseconds to just under 100 milliseconds by optimizing queries and also by using caching. This I'll be talking more about in future slides. So ultimately, if I take business value, ultimately this leads to real business outcomes with respect to cost savings, happier users, better uptime, and also faster releases. In fact, in one of the project where I have worked, we have saved almost 40% on cloud cost while handling 5 times more users simply by engineering smarter and better systems. So now that we have covered foundational framework, these are some of the outcomes we have achieved in our production systems. So first one is we have reduced API response time to 100 milliseconds by applying query tuning, optimizing caching layers, and also reducing synchronous dependencies. We brought down average response times drastically from over 400 milliseconds, 500 milliseconds to 100 milliseconds and thereabout. For example, we identified here, say, unnecessary DB joins in DB queries and also added proper indexing and introduced in-memory caching for frequently accessed data. So next outcome was basically like we throughput increase under peak load. So almost we achieved 3x improvement in throughput by removing processing bottlenecks. We used techniques like connection pooling, synchronous processing, and also refined the thread management to handle more requests per second. Even during the peak traffic, we achieved this 300% throughput improvement. And next achievement was basically 75% reduction in database table storage. So we also addressed the database storage efficiency, not just by tuning queries, but optimizing also schemas. So this included basically archiving, say, old data, removing unused columns, and also normalizing overly denormalized tables. In one case, we cut down the storage footprint of a key table, as I was saying earlier, by almost 75%. This also improved the performance. Another major win for us was basically concurrent users. Finally, we were able to scale almost to 5x. Before these improvements, basically, we were just scaling at 1,000 concurrent users. But with the same infrastructure and with the number of parts and everything, we were able to scale to 5,000 concurrent users without any degradation in performance. And the best part, these weren't basically theoretical wins for us. Basically, these we achieved in real production systems with precision. When we take a holistic approach, holistic and metric-driven approach to performance and resilience, improvements like these basically become very predictable and also repeatable. So next slide. So next slide, I would like to talk about more about query optimization techniques we used. So as system scale, in my experience, almost to 60 to 70% of the performance bottlenecks I have seen in database layer. In this basically database part of journey, we focused on optimizing the way our services basically interact with the data, both at the application layer and also a database layer. So one of the major problem was excessive database load. So we were seeing spikes in database CPU and IO during peak load, slowing down critical APIs. So much of this basically came from poorly written queries, things like fetching more data than needed, doing expensive joins, also repeatedly querying in loops. So one classic issue we tackled was n+1 query pattern. Basically, for one API call, we were doing n+1 queries. So this was killing performance. Basically, what we did was like we clubbed this entire query into one. So this improved performance a lot. So here in database, so also we created indexing and also did the query rewriting. We reviewed the most frequently executed and slowest queries during using database logs and APM tools like New Relic and also Oracle AWR reports. We added basically missing indexes, rewrote queries to reduce joins, and also avoided unnecessary queries. We used DB query hints by and also in one scenario, basically by just creating composite indexes, basically we reduced the query response time almost around 2 seconds to under 50 milliseconds. So next we concentrated on data access patterns. So we worked with the developers to analyze how data was being accessed. So if at all, suppose in UI page, if you are showing only 10 records, do we really need to fetch 100 records? So by understanding these kind of user journeys, we tuned APIs to retrieve only what actually used and needed. This basically reduced payload size and also DB load. And another part we did was we did static denormalization. So sometimes normalization basically creates too many joins. For performance critical paths, we denormalized selectively. For example, we embedded commonly joined fields directly into a reporting table used for dashboards. So this basically removed three joins and also query time was 80% faster. And also, as I was saying earlier, we focused on database specific optimizations like for Oracle. So we used optimizer hints, SQL plan baselines, and also for MySQL, basically we used explain plans to tune complex queries. So by combining application level changes with the deep DB knowledge, we cut down query volume almost by 85% in several user flows. So if you see like a query optimization might not sound glamorous, but it's one of the highest ROI efforts in performance engineering. It directly impacts speed, cost, and also user satisfaction. So next slide, I would like to talk about concurrency. So now, because handling more users is not just about throwing, say, hardware at the problem. It's about using your resources very efficiently, especially under peak load. So in this phase, we focused on how the system handled concurrent load across threads, connection pools, and also different services. So first one we did was like we did the connection pool optimization. We noticed that under load, connection saturation was leading to request delays, even dropped transactions. So we implemented dynamic connection pools, tuned just not default settings. We adapted basically to actual workload characteristics. So this alone reduced the connection overhead by almost 40% in our busiest services. For example, here, instead of having one static max size, minimum size, we configured separate connection pools for read heavy and write heavy services based on the traffic patterns we analyzed. And the next one was we moved away from blocking threads and shifted to non-blocking asynchronous logic where possible. So one service that processed incoming orders basically used to block on downstream, say, inventory calls. So we rewrote this using an event-driven architecture and decoupling the flow and improving response time even under highest loads. So we used in the code, we used basically promises, futures, and we used reactive libraries like RX Java or Spring Webflux to handle these asynchronous flows cleanly. So next, in thread management, basically thread contention is one of the hidden killers for performance for us in most of the applications. So what we did was we implemented custom thread pools, fine-tuned workloads, and also we introduced work stealing algorithms to redistribute idle threads dynamically. So we also introduced in thread management back pressure. So when the system was under extreme load, instead of cascading failures, we could shed some excess load gracefully. And another one we concentrated was timeout strategy. So timeouts, if you think, are like breaks. So the prevent runaway resource usage. So we designed the cascading timeout strategies at every level. So from database to HTTP clients, we also used circuit breakers to trip and recover services automatically if something is going wrong. This approach prevented the thread pools from being exhausted when a say downstream service failed. This maintained system stability as well. So by optimizing concurrency across all these layers, we ensured the system remained responsive even user load got spiked. This wasn't just a performance for us. Basically, it was a resiliency enabler as well. So next, I would like to talk about caching strategies we used. So when we think about scaling systems and reducing latency, a caching is one of the powerful tools available if we use that correctly. In this approach, basically we built a multi-layered caching strategy targeting every layer of the stack from client side to database. So if I talk about client side, basically we began with the front end by adding cache control headers, e tags, and also service workers. We allowed browsers and mobile apps to reuse previously fetched static data, be it images, say CS files, JS files. Basically, we versioned them and used stored on the client devices. So this reduced the basically number of hits to the server for static content, and this dropped network traffic almost by 65% for returning users. For example, here basically for user profile, images, settings, we cache them locally on the client device. So only revalidated them very periodically so that we will not show any stale data. Also, we used versioning techniques here. So next, at the API gateway level, we added the edge caching at the API gateway level. So especially for frequently accessed endpoints like product listings, configurations, and also pricing related things where they won't change very frequently. So we also built a smart invalidation mechanisms so that when the data changed in the backend, only the affected cache entries were evicted and rebuilt again. This offloaded significant traffic from the app and DB layer and also improved API response times. Next one was application level caching. So inside the application, we used a mix of in-memory cache and also distributed cache like Reddy's multi-node and Reddy's for multi-node environments. We applied the cache aside pattern where the application basically first checks in the cache and then only queries DB if the entry is not available in the cache. Also, we fine-tuned TTL values. TTL is basically time to live cache values. So based on how volatile each dataset was. So example, static config was say cached for hours, and also user session related info had basically shorter TTLs. So next, we concentrated on database result caching for expensive DB operations, large reports, and complex joins. We cached the result and invalidated it automatically when the relevant data changed. We used write-through strategies also to keep the cache and DB in sync, ensuring the consistency without sacrificing the query speed. So this helped us reduce query volume by 30% during traffic spikes. So overall, if you see caching is not just about speed, it's about control. By implementing the right strategy at each layer, we achieved better responsiveness and also scalability without compromising on data, say, integrity. So next, I would like to talk about load balancing. So if you see traditional load balancing like round robin or sticky sessions, we in this complex environments just isn't cut anymore in a dynamic and also microservices architectures. So in this phase, we implemented intelligent load balancing, which basically adapts in real time to system conditions and also traffic patterns and also service health. So first, what we did was we did the request classification. So if you see, not all requests are equal, right? So we started by classifying requests based on type, priority, and also user type. Suppose if you VIP customer is logging in, then they will get highest priority. And also we used resource, what kind of resource demand that API call requires. For example, if you see a get profile call should not be treated the same as, say, if you are doing some reporting, say monthly report request, both should not be treated as same. Here, get profile should get highest priority so that it will complete faster, and also user will not be waiting for get profile API call. Most of the times, say generate monthly report, most of the times user will be willing to wait. So we tagged the API request at the API gateway level and allowing us to prioritize and route intelligently. So high priority transactions checkout or login, those kind of transactions basically were given fast lanes. Next, we concentrated on routing strategies. So routing was basically made dynamic. So based on real-time health, capacity signals, traffic could be shifted away from overloaded or degraded nodes to healthy nodes. So we integrated service discovery with health checks so that if one node slowed down or failed, traffic would automatically reroute with minimal impact. So this strategy also helped during our rolling deployments and also blue-green releases. So next, we used, instead of equal load distribution, we used weighted algorithms based on capacity, latency, and even based on geography. For example, if one node had twice the CPU capacity of another, so it got a higher traffic weight. So we even used geolocation-based routing to reduce the cross-region network latency. So next, finally, we added continuous health monitoring with the graceful degradation built in. So if a dependent service, say search or recommendations became unhealthy, we return fallbacks or say cached data instead of failing outright. So this overall improved user experience and also this helped immensely during partial outages. So together, these techniques created a smarter, self-aware load balancing layer that maintained performance and also uptime, especially during failure scenarios and also peak traffic events. And because it was all observability driven, we could tweak and improve routing strategies based on real telemetry we used. So next, I would like to talk about observability. So when systems grow in complexity, if you see visibility becomes non-negotiable. Without the right visibility in place, even small issues can become major outages. So we built a comprehensive observability platform, one that basically combined metrics, logs, traces, and alerts into a single cohesive feedback loop. So if I talk about metrics gave us a high-level view of how our system is behaving. So we used two proven frameworks. One is RED, that is RED, rate, errors, and duration. This is basically great for services and API monitoring. So another framework we used was USE, utilization, saturation, errors. So this framework is basically ideal for infrastructure and resource monitoring. For example, by tracking request rates and latency across services, we spotted bottlenecks long before they even caused downtime. So we also tracked business KPIs like say card conversion rate or average transaction latency. So teams could correlate technical changes to user impact. So next, logs. So metrics, basically if you see like metrics tell us something is wrong, but logs tell us why that is wrong. So we standardized our structured logging, so including error codes, request IDs, user IDs, and also we logged relevant payloads. So with the correlation IDs, we could trace a single user request across, say, dozens of microservices. And also we enriched the logs with the contextual data like a region, environment, and also feature flags to make debugging faster. So next, traces. So if you say, if we implemented distributed tracing using tools like OpenTelemetry or Agar, this allowed us to visualize how a request flowed across multiple services from front end to back end and see exactly where delays occurred. For example, we identified 60% of latency in checkout flow came from a downstream payment system. So we would not have caught that with logs alone. So here basically traces helped us. So next, alerts. So instead of say noisy threshold based alerts, we used SLI and SLO driven alerting, which only triggers when say actual reliability goals are at risk. We also implemented alert correlation so that a cascade of downstream errors would not overwhelm support engineers with redundant notifications. So this led to fewer false alarms, better on-call experience, and faster resolution time. With this observability framework, the end result is basically we gave engineering teams near real-time total visibility into their services, making it is easier to spot, investigate, and also fix issues before users even notice them. And just as importantly, we tied all this observability back into business goals. So every alert or dashboard was rooted in real impact. Next, I would like to talk about data-driven capacity planning. So one of the biggest challenges in any large-scale system is balancing cost with performance. So if you over-provision, basically that leads to into higher or unnecessary cloud spend. But if you under-provision, basically you may face outages as well. So our answer to this is data-driven capacity planning. So first, what we did was like we started the deep analysis of historical utilization, looking at CPU, memory, IOPS, and also network usage across services. We profiled each component and identified seasonal traffic patterns. For example, most of the times usage basically surges on Monday mornings or traffic spikes occur during end of quarter events. We also built anomaly filters to distinguish between real spike or one of the spikes, a random spike. So we would not scale infrastructure based on outliers. So this helped us establish accurate baselines for each environment and also each service. So next, we did growth modeling. So we applied statistical models and machine learning to forecast how usage would evolve based on, say, product growth and also business events. We factored in new feature rollouts, marketing campaigns, and also customer onboarding timelines. For example, we modeled several scenarios. So first one is best case scenario, what is worst case scenario, and also what is, say, expected scenario. Each we associated with the confidence levels. So this gave product and also infrastructure teams a shared and also data backed plan they could lean on. So next, resource optimization. So based on those projections, we implemented the dynamic scaling strategies across services and also infrastructure. So we used Kubernetes horizontal pod autoscalers and also cloud native scaling policies for database and also messaging systems. We also defined resource utilization targets, so services would scale only when truly needed and scale back when they are idle. So this approach allowed us to strike the right balance between performance, headroom, and also cost efficiency. In one case, we reduced monthly cloud spend by almost 30% while maintaining 99.99% uptime just by optimizing our provisioning strategy. So key takeaway from this is the capacity planning should not be a guessing game. So when it's a data-driven, predictive, and aligned with business growth, it becomes a strategic advantage. So next, I would like to talk about performance testing, which is crucial. So in traditionally, if you see like performance testing has been seen as one-time phase at the end of the product development life cycle. But in modern delivery pipelines, that approach does not work anymore. So we treated performance testing as a first-class citizen with CI/CD from the smallest function to full-scale load test. So first, unit test. So we started with unit level performance test. These are basically fast, lightweight benchmarks embedded directly into builds. If your core function, say a pricing calculation, suddenly slowed down by 2x, we could catch it immediately during a pull request. This helped us developers fix regressions before they reached integration or staging environments. So next we did service level isolated testing. So each microservices service basically had its own performance benchmark suite. So running in isolated environments. This we ran in isolated environments. So we measured the service level latency, throughput, memory usage, and also error rates in controlled conditions. So we used mocks here to simulate, say, downstream systems. So this allowed teams to independently tune their services without needing to test the entire system every time. For example, a catalog service could be validated against a known data set also or known mock endpoint for consistent response times for different load scenarios. So next we did integration performance testing. So when we then tested across basically multiple workflows, how this basically tell us how services behaved when chained together. This revealed issues like cumulative latency, serialization bottlenecks, and also inefficient retry logics. So in one case, a checkout flow that fine in isolation almost showed a 2-second delay when we tested it end to end. The culprit here basically was a synchronous email service holding up the complete flow. So next we did full-scale testing in pre-production environment. The environment was production-like environment. So we finally, before any major release, what we did was like we ran production-like load test in pre-prod environment, simulating real traffic patterns. So with realistic data and also concurrency. We used tools like JMeter, Gatling to mimic user load across geographies. So those results directly mapped into SLOs. So if any service missed its latency or error target, the deployment was paused automatically. By integrating performance testing throughout the pipeline, we shifted the left and caught performance regressions before they reached production. This not only improved reliability but also built confidence across teams that every release was truly ready for scale. So, up until now, we talked about optimization, scaling, and efficiency. But what happens when things go wrong? Because in real world systems, failure is basically unavoidable. So, that's why we introduced chaos engineering, a discipline that lets us prepare for failure before it actually happens. So, in for chaos engineering, first what we did was like we did the hypothesis formation. We started basically by forming clear, testable hypotheses about how the system might fail. For example, if the say inventory service goes down, can checkout still succeed using cached inventory data? Or say if database latency spikes for 30 seconds, will the user session expire gracefully or degrade the performance? We focused on these tests on critical business flows, sign up, login, checkout, and also on data ingestion. Once a hypothesis has been formed, we experimented the design. We designed experiments to simulate real failure modes. That could mean as a sometimes killing a pod or injecting a latency or simulating a dependency failure. The key was here control. We scoped the blast radius and applied it in isolated environments first, and then monitored every step. So in one case, basically we introduced 30 seconds latency to our payment provider integration. and watched how our, say, retry policies handle this. We executed this test progressively in controlled manner, starting in dev, moving to stage, and then selectively into production using canary deployments. Each experiment had auto termination criteria. If key metrics like error rate or latency crossed safe thresholds, the test stopped immediately. This ensured we did not cause actual harm, especially in production, while uncovering real risks. Next one is most important thing. We did not stop at discovery. We converted findings into actions. We added circuit breakers where needed, improved retry logic, and also made our fallbacks smarter. For example, after one test, it revealed a slow downstream search API stalling the home page. We implemented a timeout plus a cached fallback, cutting failover time from minutes to seconds. We also automated many of these recovery patterns so systems could self heal instead of waiting for a human intervention. So, if you see overall, chaos engineering gave us a proactive resiliency mindset. We stopped fearing for failure and started designing systems that could withstand and adapt to it. Thank you. This is about my session. Thank you all for being here and taking time to explore this journey with me. We have gone far beyond just tuning response times or adding few dashboards. What we have seen here is a complete layered approach, one that brings together architecture, code, infrastructure, and also automation. By engineering with reliability in mind, right from the ground up, we can build cloud native systems that are not only fast and scalable, but resilient by design. My hope is that today Stock sparked new ideas for your teams can shift left on performance and also break silos and develop systems that perform well. Thank you again for joining with me.